Okay, I think it is afternoon, I suppose. So good afternoon, everybody. Thanks for coming here. My name is Archis Ghate. I am the general chair for this conference this year. So I'm here to introduce our tutorial speaker, Professor Amy Ward, who is a Rothman Family Professor at the University of Chicago Booth School of Business. Amy received her PhD from Management Science and Engineering at Stanford, which is where I actually went. And her expertise is really in service operations management, and especially with a focus on stochastic processes and decision making within the context of stochastic models and processes. So please join me in welcoming Amy here for the tutorial.
Thank you.
Okay, thanks.
Okay, so good afternoon. I'm going to speak on scheduling an overloaded multi-class queue with impatient customers. This is joint work with Amber Puha, sitting in the audience in about the 4th row. I want to start by asking the question, why do we care about scheduling? And can everyone hear me? Mic's okay? Great. So why do we care about scheduling? Scheduling has a first-order effect on customer wait times. So here's a situation with which we're all familiar. At least I experienced this coming to this conference. Think about an airline's first-class check-in and the economy check-in. The first-class check-in rarely has waiting, and the economy check-in often does. The first-class customers are given a priority, and that's an example of a scheduling policy. Let me contrast this with a situation where you've got the exact same number of agents helping you, but there's no priority. You're just going to serve people in the order in which they arrive. If you do that, everybody's going to wait a little bit, so your waiting is sort of evenly distributed. So I'm using this as an example to illustrate that scheduling is a way to distribute your waits. And so that's a first-order way to distribute your wait times. That's why we care about scheduling. And it's not true just in this airline check-in context. This observation is true in basically any situation where we see scheduling decisions being made. So for example, in the OM literature, we've seen this. There's a call center survey paper. There's a book that shows scheduling decisions in the context of computer systems. I've also mentioned a book where you see scheduling decisions in hospitals. And I've referenced a generic scheduling book. There are others. This is some recent things. Right, so let me start with a simple scheduling problem. The simplest thing I can imagine, almost. I have 2 jobs. One has a processing time of V1, that's a deterministic processing time, that's the blue job, and a holding cost of C1. The gray job has a processing time of V2 and a holding cost of C2. The objective is I want to determine the schedule that minimizes the holding cost. So I have 2 options here. I do 1-2, or I do 2-1. If I do 1-2, the cost of that, well, class 2 job, he's the one that has to wait. He has to wait the amount of time it takes me to process V1. So that's V1. And it's a per unit time waiting cost or holding cost there. So that's C2 times V1 is the cost. Similarly, if I schedule the opposite way, I get C1 times V2 as the cost. Which schedule am I going to choose? I prefer the schedule 1-2. If and only if the C2 V1 is less than C1 V2. Or equivalently, if C1 divided by V1 is less than that's just a typo, that should be, this is a typo, should be C2 divided by V2. The reason I made that change is many of you may be familiar with the CMU rule. The CMU rule is a popular scheduling rule. This is the CMU rule if I let mu I equal 1 over VI. So mu I, I'm thinking of as the processing rate. If VI is the processing time, 1 over VI should be the processing rate. The CMU rule ranks the classes in the order of their C times mu value. And it serves the class first. It gives priority to the classes with the highest CMU values. So this is a very simple rule. It's easy to implement. And it's optimal in this setting. The rule is very appealing. Okay, so some references. Now this is a deterministic setting. I'm interested in stochastic settings. If I think about service systems, I usually don't know when customers are going to arrive. There's some variability or randomness in there. So my question then is, does this very nice simple rule have optimality properties when I have stochasticity or randomness? What about stochastic systems? So the answer is yes. So there's several stochastic settings in which the CMU rule is optimal. So in the Pinedo paper, there's a fixed number of jobs, and arrival times and processing times are random. In contrast, in the Klimov paper, it's not a fixed number of jobs, it's jobs that are arriving over a time interval. I don't know how many will arrive. You can think of a renewal process, or it's a Poisson process in this model. So this is sort of a more standard queuing situation. And I'm really interested in scheduling and queuing situations. I don't know exactly when the jobs arrive. I don't know exactly how much processing they'll require. And you start to see from this literature review that the CMU rule has optimality properties more widely than in the simple deterministic setting that I gave you. Now, CMU can also be extended to have convex delay costs. It doesn't have to be strictly linear. And I have this generalized CMU is asymptotically optimal. So what happens in generalized CMU? You have some kind of convex delay cost. When you need to decide who to serve, you look at the derivative of your delay cost function. You rank the classes sort of according to that. So in a linear case, it's just going to be the C. And you have this index rule, but it's a state-dependent index rule. So again, I've got some optimality properties. I'm not going to say exactly the setting where I see them as asymptotically optimal, but I'll call it nearly optimal. It's not a mistake that if you look at the two papers, one says strictly convex and one says convex. So we're starting to get a little bit comfortable that this very simple and appealing rule has nice optimality properties, which makes me want to use it. But then there's this but, that the CMU rule can also have disastrous performance. And that's true when delay costs are linear. And I think the intuition for that is the mini servers can be trickier. So in the mini server setting, if you do a scheduling policy that induces some idleness, that can be really bad for you. So you have to be a little bit more careful. Now, the other thing I want to do is there are many service systems where customers are impatient. So I just showed you some results where customers will basically wait indefinitely. But often, jobs or customers, they have deadlines. They're not going to wait indefinitely. And if I don't process them within some amount of time, they're going to leave. And I'm actually never going to process them. I'm just going to lose them. So what happens when I have impatient customers? And that's the setting I'm most interested in. So I see some reasons for caution when I have impatient customers, because all of the following papers only sometimes recommend CMU. But then there's this really nice hope, because I have a paper by Atar, and Chimkin, and it recommends a modification of CMU, CMU theta. Theta is a parameter controlling how fast customers will abandon. The point is CMU theta, which I will describe in a minute, is still a state-independent simple index policy. And the Atar, and Chimkin paper shows this is asymptotically optimal in a mini-server overloaded setting with linear costs. So if you want to think about a difference here, I have mini-servers critically loaded. Critically loaded means my demand is approximately equal to my system capacity. Overloaded means my demand is more than my system capacity. So I'm going to start to get hopeful again that if I'm in an overloaded setting, I'm back in a situation where a simple index CMU type rule will work. And let me explain a little bit more carefully exactly what we know. So I'm looking at a multi-class MMN plus MQ. What does this mean? I have J classes. The arrival rate to each class is determined by the lambdas. The service rates, okay, so the colors are representing these different customers in class in service with the server. The service rates are determined by the muse. They can be class dependent and also exponential. So exponential inter-arrival times, exponential service times, and exponential abandonment times. So the theta, or 1 over theta, is the mean time to abandon. If I'm not served on average within a time of 1 over theta, I will leave. Otherwise, I will be served. There's two costs in this system. There's a holding cost, that's the C1, and there's an abandonment cost. If I lose a customer, the cost per customer I lose is the abandonment cost. So my scheduling question here is, who do I next serve? The Attar, Giat, and Shimkin result tells me that the C mu divided by theta rule asymptotically minimizes long-run average cost in the overloaded regime. So let me pause for a second. So C mu divided by theta, I'm ranking the classes in the order of their C mu divided by theta. The class that has the highest priority is the one with the largest C mu divided by theta value. It's the C mu rule, except I'm modifying it with these abandonment times. The C tilde comes in because remember before, customers didn't abandon, I only had holding costs. Now that customers abandon, my cost structure should really include an abandonment cost. So the AJ is every customer that abandons is costing me AJ. Theta J AJ is my cost per unit time. So this C tilde you can think of as a cost per unit time. Couple things to notice to give you some intuition. So if theta is all the same, then it's going to reduce to a C mu type ranking, if theta is all the same and I don't have any abandonments. On the other hand, if I don't have any holding cost and I just have abandonment cost, the thetas are going to drop out and I have an A mu rule, and the order in which I serve customers is going to be the class with the highest A mu, abandonment cost times service time. So I think that's a little bit of intuition there. Makes a little bit of sense. Now, the focus of this tutorial is general distributions. And my key question is, do the Markovian assumptions, do the fact that I have exponential distributions affect the form of this asymptotically optimal policy? And by asymptotically optimal, I'm looking at this overloaded setting, so have a little bit more demand than capacity. And I specifically want to think here, do I have a state-independent priority ranking? So when I say C mu, I'm thinking I have a state-independent, not the generalized C mu, not a state-dependent index thing, but a state-independent priority ranking rule. That's what I'm looking for. And the spirit that I'm doing this in is we're often using exponential distributions, even though that might not be the best distribution in your application, because we hope the form of the policy is preserved. And it's a lot easier to derive the form of the policy under the exponential assumptions. And I'm hoping for robustness. If the form of my policy that I see with exponential distributions hold when I remove that exponential assumption, now I have a restricted policy space to start thinking about. So that helps me. So that's what I'm looking at here. The E's now, totally general distributions, they're counting processes. They could have time varying rates. I'm not putting any assumptions there except that they're counting processes. These service distributions are general distributions. So the idea is a customer arrives, I take a draw from this GS. S is mnemonic for service. And that's the time that he requires to be served. The G1R, the R is mnemonic for reneging. I'm going to say patience time distribution a lot because I'm thinking of the patience time of the customer. But sometimes I'll say patience time, sometimes I'll say abandonment time, sometimes I'll say reneging time. They're all the same thing. The customer samples from this distribution. If he's served within that amount of time, he will get served. If he's not served, he will leave the system without being served. Okay, so what am I interested in? My key question, do I still have this state-independent priority ranking when I remove my exponential assumptions and go to much more general model? The first thing you're going to notice is I actually don't even know how to approach that problem. Okay, so when I had the MMN plus MQ, I could think about putting this in a Markov decision framework. And maybe I can't solve it exactly, but I can certainly do some numerics. Now the control problem, and writing out the control problem, seems pretty tough. So the methodology we're going to be working with here is I'm going to show you the fluid model. The fluid model means I'm going to remove stochastic variability from this system. It's going to be a deterministic model. We're going to understand what should the fluid model be. I will show you a theorem that connects between the stochastic model, the stochastic Q, and the fluid model, which is deterministic. Why do we care about this? So we care about this if I look at the fluid model and I look at the fluid invariant states. The fluid invariant states are happening as time goes to infinity. So you can think about your fluid invariant states as an approximation for mean, like mean Q length in my stochastic system. So if I can get you a nice and analytically tractable expression here, I can now set up a control problem because I can make a link between my scheduling control and what types of queues I will have in each class. So that's what I'm going after. My methodology to go after it is we'll look at what the fluid model is, then we'll look at the fluid invariant states, then we will see what is the fluid control problem that lets me optimize over the scheduling policy to be in the, quote, best invariant state, which basically means finding the mean queue links that minimize my costs in this system. Is that clear? Okay, so this talk we're focusing on the fluid model. There's also a technical paper with Amber. She talked about it yesterday. And a couple times I'm going to be referring to results from the technical paper. We're not going to talk in detail about them, but I want you to feel comfortable that what I'm doing here is supported on rigorous mathematical footing. We're not just going off into outer space here. Right. So we're about 20 minutes in, and I can also give you the talk outline. So I want to start out, and I want to talk about what is the state space of this stochastic model? What is the state space of this queue? That will help you understand what I need to track and why this is so difficult to even think about as a control problem. Then we're going to talk about the fluid model. Then we're going to see how to characterize the fluid invariant states. Then we're going to see how to use those to write a fluid control problem. Then we're going to solve the fluid control problem, and we'll get a scheduling policy. And we're going to link between the solution to the fluid control problem and what is a good scheduling policy for your system. And we're going to see, this is where you pause and think about my motivating question, does the solution to this fluid control problem motivate static priority or not? At the end, I'm going to talk a little bit about non-overloaded systems. If I have time, I will do this. We'll see how the time comes out. And I will explain to you something we noticed at the very beginning in the literature, which is it looked like whether or not your demand and capacity are approximately in sync or whether or not you've got this overloaded setting might determine whether or not this nice, simple, state-independent ranking is going to work for you or if it's not going to work for you. Okay, so what is the state space here in this system? I need to track 4 things. The vector of times since the last arrival of each class. The x, this is the vector of the number of customers in the system of each class. The nu and the eta are vector of measure-valued processes tracking the age in service and the potential queue of each class. We're getting this state space description. It's first observed in the single class setting, that this is the useful state descriptor. So we're leveraging off of that. What is this nu in this eta? I think it's helpful to see this in pictures. So nu is my age and service measure. I want you to picture you have these customers waiting. You have this x-axis. Each dot is representing a customer. And the position is, I said waiting, customers in service. Sorry. Each dot is representing a customer. The customer is in service. The position is how long that customer has been in service. So each dot is a unit atom whose position represents the time elapsed since a customer began service, and it shifts to the right at rate 1. The customer ending service has age 0. I don't track the customer anymore once the time spent being served exceeds that customer's service time, so he will drop out. From this measure, I can get at useful quantities of interest. So for example, if I want to know the number of customers in the system, I'll call that as bj, I'm going to integrate over this measure. Nu j of t is my measure at time t. I'm going to integrate over the state. So what this means is basically I am counting the number of dots that you see on this axis. 1, 2, 3, 4. Okay? The hj of s is the upper bound on the support of the distribution. So this is telling me if I have the new measure, I can get at how many customers are in service. The notation I'm going to use for that is this bracket notation. So the 1 is a test function. The nu then is the measure that I'm integrating against. So that's my notation. The other measure to talk about is the A to J measure. The eta j, I'm going to call the potential Q measure. Again, each of these dots you can think of like a customer, but slightly different interpretation. I'm tracking waiting times. So each dot is a unit atom whose position represents the time elapsed since a customer arrival and shifts to the right at rate 1. So the customer entering the system has waited 0 time units. The customer is no longer tracked once the time elapsed since arrival exceeds that customer's patience time. Something to note here, I didn't say anything about scheduling or going into service. And I think this is kind of the genius that we took from the Caspian Ramanan and Kang and Ramanan papers that you saw before. The fact that it's independent of the scheduling control makes things a lot easier for me to analyze. Certainly the new measure, the number of people in service, that is heavily dependent on your scheduling control. This one's not. All this one is going to do is give me an upper bound on the number in Q. So if I integrate over this measure at time t, I'm going to get an upper bound on the number in Q. That's why I call it the potential Q measure. So you may be asking, how does this help me? So let's think about this. This is where I have an assumption that each class is served in a head-of-line fashion. That's where this assumption comes into play. So my head-of-line customer, that's this orange guy. Let's say chi j of t is the wait time of the class J head-of-line customer. Well, the dots to the left of this guy, this one, they are actually in queue. They're not potentially in queue. This guy is in queue and he's waiting. The dots on the other side, they have either entered service or they've entered service and departed. The only thing I know about anything I see in this measure is that the abandonment time has not left. The dropout time for the atoms in this measure is when the abandonment time expires. So the head-of-line customer is giving me a nice division where I know on one side, this is my actual queue length. On the other side, these are guys that maybe have gone into service. And so what does that mean? So, right here, sorry. So that means if I want the number actually in queue, I'm going to integrate this measure up to the chi j of t, the wait time of that head-of-line customer. And that gives me a way of getting at the number of customers actually in queue. Okay, so recap. If I want to look at the number of class J customers in the system, I can integrate against this eta j measure. That should equal xj minus the number of customers in service. That's determined by the new j measure. And I know that that is upper bounded by this number potentially in Q. Another recap, 3 primitive inputs to this system. There's the arrival counting process. That's my EJs. There are sequences of IID service times for each class. They're drawn from absolutely continuous GJS. There are sequences of IID patience times for each class drawn from absolutely continuous GJR. I'm not going to show the detailed evolution dynamics for the stochastic model, the stochastic Q. I am going to show them for the fluid model, the deterministic approximation, which is easier. So let's look at how this system evolves in the fluid model. So what are you thinking of the fluid model? The fluid, you're imagining that I don't have discrete customers. I have fluid flowing into this system. I will show you the scaling at the end, but the scaling is basically there's a lot of servers, and the demand is large. And if I divide things by n, that's going to give me a situation where instead of thinking about individual customers, I can think of the customer classes as fluid flowing through the system. And I can think about the server, what's in service, as an effort devoted to each class. Okay. So the fluid model state space is going to be on the set of right continuous functions with left limits, x, nu, and eta. I dropped out the alpha because it's fluid. I don't need to keep track of these residual arrival times anymore. And I guess to understand RCLL, you need to know a little bit about the topology. So just briefly, I'm looking at a product space. The x is a vector in Rj and has the usual Euclidean topology. The nu and the eta are coordinate-wise finite, non-negative measures on the non-negative real line, and they have the usual topology of weak convergence. Now let's see how this system evolves. And you should also note that I am reusing notation in the sense that x, nu, and eta are now in fluid space. They're not the stochastic model. So slight abuse of notation here. So what can happen? How does the dynamics evolve? These are my auxiliary functions. And I'm calling them functions to remind you that everything's deterministic. So Bj, we already saw this. This is the proportion of class J fluid in service. Dj, this is my cumulative departure function. Where is this coming from? So nu j of u, that is the amount of class J fluid in service. So let's think about how much is going to depart in the next little bit of time. Well, that should be controlled by the hazard rate function. So that's where this hazard rate function is coming into play. And then I'm integrating over 0t because it's the cumulative departure process. Oops. And you can see that this finite condition is now related to the fact that I'm not allowing an infinite amount of fluid to depart. That sort of makes sense. That's a finiteness condition. Qj, well, Q should equal the amount of class J fluid in the system minus the amount in service. Chi j we saw before. Chi j is the class J head of line wait time function. Rj is the cumulative abandonment function. And let's look at this. This should be reminiscent also of what we saw before in the state space. Eta j, this is my potential Q function. I'm only integrating up to chi j, so that's just getting me the amount of fluid that's actually in Q, not potentially in Q. And if I think about if any of that fluid is going to leave in the next little time instant, that should be controlled by the hazard rate. So that's where this is coming from. The last bit here, the cumulative entry into service function, well, that had better equal, if nothing's disappearing, the amount that's departed plus anything that's in service, maybe anything minus anything that was there initially. Fluid model solution, not unique. Something you might notice is that I'm not actually specifying a service rule. That might seem a little bit odd, but what do we want to do? We want to figure out what the service rule is that minimizes our costs. So I probably shouldn't specify one at the outset. So that's why you see not unique. If I haven't specified a service rule, we can't really expect uniqueness here. So let E be an arrival function. This is telling me for each of the classes, what's the pattern of fluid coming into each of these classes. Then the x nu eta is a fluid model solution for E if, for each j, my kj is non-decreasing, and the kj is such that the amount of fluid in service does not exceed my service capacity. So I'm not specifying the service rule, and this kj, to keep in your head, the kj is connected to your scheduling policy. So there's a connection between your scheduling policy and your kj. Oops. The next, so for all j and t, I have some kind of mass balance. The total number of customers in the system should equal the number there initially, plus, I said number, I seek amount of fluid, plus the amount of fluid that's arrived, minus the amount of fluid that has abandoned, minus the amount of fluid that has gone through service. The Q links have to be always less than or equal to the amount of fluid that is potentially in Q. And the last two equations are giving you how the measures evolve. So let's think about just a little bit of intuition there. And I think the intuition is best if you think about the F function as being just an indicator function, so just one, or not indicator, F is just one, the identity function. So the first term here, the first term is describing what happens to fluid initially present in service. So for the fluid initially present in service, that's the nu J0. This fraction here is giving the probability that fluid present for X initially, because the initial measure will tell me how long all of that fluid has been there, is still present in time X plus T. So that's the first term. That's telling me what's happening to the fluid initially present in service. What about this second term? Kj is the scheduling rule that's regulating when fluid is going into service. So the second term is describing what happens to fluid that enters service after time 0. And what's happening there? Well, if the fluid entered service at time u, what's the probability that it's there t minus u time units later? Well, it is your complementary CCDF function. So this is 1 minus GJS. So that should be the probability that the fluid is still in service after time t minus u, that the service requirement exceeds t minus u. A similar intuition helps me describe this second evolution equation for the eta. There's a theorem behind this. So there are two things going on. One, I want you to realize that there's a rigorous connection to what I'm showing you. The fluid model is really rigorously connected to our stochastic model. The second is, if you were wondering a little bit, what's this scaling she was talking about, how does the fluid model come out, you can see that. So it's a law of large numbers scaling. We're assuming that the number of servers is getting large, and my arrival rates are being scaled by the number of servers. So the amount of demand you have is on the same order as the number of servers you have. And we're assuming that there's some kind of law of large numbers at the process level, so functional law of large numbers. Also have an assumption on the expectations. The other bit here, this is saying that that fluid model I showed you is going to be good for most any scheduling policy, but you can't do something too crazy. So no wild scheduling policies. You can't ignore everybody for 1,000,000 time units and then decide you're going to bring a huge chunk of stuff into service. No wild oscillations. We need a convergence of initial conditions, mild condition on the hazard rates of the abandonment and service distributions, and we need some continuity in that arrival function. Then what we know is that if you have a distributional limit point of a sequence of fluid-scaled state processes, then x nu eta is almost surely a fluid model solution for E with continuous auxiliary functions. So I have a tightness result in the background. The tightness result is giving me the distributional limit point. This theorem is in the technical paper. I'm showing you this to give you a rigorous connection between the fluid model I showed you and the stochastic model that is where our scheduling problem is actually existing. A little bit of related literature. Of course, we didn't do everything on our own. We're building a lot on what's happened in the single class case. So work on the single class GGN plus G fluid model provided the framework for the multi-class case. The fact that the first is a G and the second are GIs, that's not a typo. I'm emphasizing the fact that the arrival process can have time varying in it. The service and the abandonment process are all sequences of IID random variables. So there's more generality in the arrival process than the service and the patient's times. So Witt proposed the fluid model. Liu and Witt showed how to calculate some fluid performance measures. Reed and Caspian Ramanan proved convergence without abandonment. Kang and Ramanan proved convergence with abandonment. Long and Zhang show convergence to invariant states under restrictive conditions. The only reason I put that in there is you're going to see that one open problem is I will characterize invariant states for you. I will not prove convergence. It's tough in the single class case, so it might be a lot to ask in the multi-class case, at least right now. Work on the multi-class GGIN plus GI fluid model is more recent. The closest paper here to us is Attar, Caspi, and Shimkin. They analyze the static priority scheduling. Think about my motivating question. We want to know, we want to have a richer class of scheduling policies. At this point, we don't know that that's the right thing to do. So our technical paper extends to non-static priority scheduling. What we're doing here is understanding how that helps you for the fluid model. Okay, fluid model invariant states. So where am I? We've got this scheduling problem. We're hoping we get a nice index rule coming out. We don't know because this model is hard to analyze. What do I need to do in order to formulate an approximate scheduling control problem? I need to understand what the fluid control problem is. The fluid control problem is based on these fluid model invariant states. You can think about the invariant states as a fixed point of the fluid model equations. So we're looking for a fixed point of the fluid model equations. We want something that stays constant over time. And we want this because then we can formulate a fluid control problem that lets us answer our question about the scheduling policies. Okay, so let's talk about the invariant states. Fluid model invariant state, I'm going to draw it back to constant arrival rate. So I think there's more generality. You can think about scheduling problems when you have time varying arrival rates. That's why I wanted to show you the more general fluid model. However, for our scheduling policy, for our original motivating problem, we have constant arrival rates. So I'm going to start with that. Okay, so I have constant arrival rates, I have a finite mean patience time, my 1 over theta j you're interpreting as my mean patience time, even though I don't necessarily have an exponential distribution there. The definition is a tuple x star nu star eta star is an invariant state if the constant function is a fluid model solution. Okay, so the process stays constant over time. That's the way to think about it. And for any invariant state, if you see the stars, anything I superscript with star is going to mean that that's associated with the invariant state. So these are the auxiliary functions associated with my invariant state. So I need to characterize invariant states. This is my theorem to characterize invariant states. Conditions I need is I need to add one more condition. My patience time distribution needs to be strictly increasing. We already assumed it was absolutely continuous. I have an inverse function. Okay, let's think about what is the feasible set of server allocations. What do I need to do to solve this scheduling control problem? In fluid space, what it means is I need to know what is the fraction of server effort that I want to devote to each class. So this B is a vector that's telling me the server effort allocation to each class. Rho j, lambda j divided by mu j, that's the workload coming in from each class. So if you think about this B, this is the feasible set of server effort allocations. There's no reason to serve more than the workload because then I'm just wasting server capacity. And the sum of these BJs needs to be less than or equal to 1. Okay, so for any B you're associating with your scheduling rule. I have not yet told you how to go back and forth between B and the scheduling policy for the stochastic system, but I will. For right now, you have to trust me that if we find a B, I can tell you a scheduling policy that you want to use in that stochastic system. Okay? So B is somehow is linked to my scheduling policy. B is also uniquely defining an invariant state. So that's what's happening in this theorem. So you give me a B, and I have something that satisfies these 3 conditions, which I'll talk about in a minute. Then the x nu eta defined by this 1, 2, and 3 is an invariant state, and conversely, if I have an invariant state, then that invariant state is going to satisfy 1 through 3 with B equals to B star. Now, what are these 3 conditions? So I was emphasizing that I have an if and only if here. Okay, the first thing to explain, I think let's look at this Q, because this is important for our control problem. The Q length of class J is determined by Bj, the effort allocation you put in there. What's happening? The numerator, lambda j minus Bj mu j. Lambda j is the amount of fluid coming in. Bj mu j is the effort devoted to that fluid. Lambda j minus Bj mu j, that's the amount you must be losing. So inside this Fj function is the percentage of fluid that you're losing. What is Fj? Fj is defined in terms of your patience time, the inverse function of your patience time distribution, and your excess life distribution. So for excess life distribution, it's probably easiest to define if you think about a renewal process. It has an inter-arrival distribution of GJR. The excess life distribution is your stationary initial delay. I realize that right now this formula for the Q is not particularly intuitive. I'm going to give you a little bit more intuition on the next slide. What I want you to recognize right now, here's the important thing to recognize. This is a very analytically tractable formula. It is a closed form expression that connects between your effort allocation of each class and how much you have in Q. That's what you need to write out a control problem. Okay? So that's the main thing to be getting here. Right now you're saying, okay, this is very good. I have a very nice analytically tractable formula for what my Q links are for any given server effort allocation. What is the rest of this? Well, if I'm thinking about an invariant state, I'm defining the eta measure, the nu measure, and the x. So the x is going to be the B, the amount of fluid in service, plus what's waiting, that's the Q. We just talked about this. What's the intuition for this eta measure? Well, the intuition for the eta measure comes from realizing that fluid from class J is coming in at rate lambda j. So that's the rate that fluid is entering. And this complementary CDF dictates what proportion has not reneged X time units after it's entered. So that's where that's coming from. What about this new J? There's something very intuitive in this new J if you look at it. So Bj mu J is the rate at which I'm serving class J fluid. So if that's the rate at which I'm serving class J fluid, it better be that the rate at which class J fluid is entering service is Bj mu J. So that's the Bj mu J, and then the 1 minus Gj S of X has a similar interpretation. That's the complementary CDF. It's telling me fluid that's entered service, how long is it going to stay? That's how long it's going to stay. Okay, so a little bit more here. Before I set up the fluid control problem, I want to say a little bit more about intuition for the invariant states. And I want to say intuition for the invariant states, and I also want to show you some graphs so that you can be convinced that these invariant states are actually have predictive power. Because if they don't have predictive power, they're not helpful. Okay, so some intuition. I think the first intuition to think about is what happens if your patient's distributions are exponential. We should make sure that we're consistent with what should happen in an exponential case. So suppose, in this case, your excess life distribution equals your cumulative distribution, which means this Fj is just the identity function. So that tells me that my Qj is lambda j minus Bj mu j. That's the amount of fluid that's eventually abandoning. And 1 over theta j is the time it's staying before it abandons. So that sort of makes sense that that should be your invariant state for the Q links. Another thing to notice here is it satisfies a nice flow balance equation. So if I bring the theta j to the left-hand side of the equation, I get a Qj times theta j. Qj is actually constant, so I don't need that t there. This is the rate at which I lose fluid. Theta j is the rate at which stuff is abandoning. Qj is the amount of stuff I have in there. So this is the rate at which I lose fluid. And what's the fluid that's not served? Well, it's the difference between what arrives and how much is being served. So this is how much I have to lose. So this should be equal. Now, what happens when I go from away from the exponential distribution? Why is this getting more complicated? So this part is not true for non-exponential patience distribution. So we're creating nonlinearities when we move away from the exponential patience distribution. Why? So what's happening there? So the willingness to wait of a customer is changing over time. If you think about this, as customers wait for their service, some become more patient, for example, as a result of having already paid a waiting cost, and some become less patient, for example, as a result of being frustrated from waiting. So if you think about it that way, this isn't going to hold. We are going to need some kind of nonlinear approximation for that Q length, and that's exactly what's coming up. And so the contribution here is to characterize what exactly is that mapping, what is that function. Let's also do an example invariant state calculation. I want to convince you that these formulas are reasonably tractable and easy to work with. So let's suppose the class J patience distribution is uniform, and I've set it the uniform parameters, so my mean is 1 over theta j. Okay, so this is my cumulative distribution. I can take the inverse cumulative distribution. I can also calculate the excess life distribution. So it should be 1 minus the cumulative, and this is times 1 over the mean patience time. So that's how I'm getting this. Now I do a little bit of algebra. Okay, so now I can calculate this Fj function. If I can calculate the Fj function, I can calculate my prediction for the Q length as dependent on the server effort allocation being given to class J. So that's my Qj of Bj. So I do a little bit of algebra here, and I get this function, which you can clearly see is nonlinear in Bj. So first, you can clearly see it's nonlinear in Bj. Second, you can see that it's something that looks pretty possible to work with and probably something I could use if I'm trying to do a maximization or a minimization problem. There's still this question, and let's pretend you didn't understand anything I said so far. The only thing you need to understand right now is I have a formula to predict Q links. I have a formula to predict Q links, And it's tractable. It's an easy formula. So what do you want to know? Does my formula work? Okay, so let's see if my formula works. If my formula works, then you can forget everything else. All you need to focus on is the fact that you have this approximation formula for your Q-links, and you can use that approximation formula to set up a control problem. So here's my evidence slide that my approximation formula works. I'm only showing you one simulation. There are others. We're looking at a two-class queue, exponential arrivals, log normal service, and log normal patience time distributions. So this is not something that I have any hope of solving for performance measures like expected queue links or wait times analytically. It's a static priority scheduling, so I'm fixing the scheduling policy. And each class has arrival rate of 60 per hour. So it's overloaded. My total amount of customer demand is 60 plus 60, so 120. My total service capacity is I have 100 servers. Each approximately, it's one time unit is the average service time. So I've got service capacity of 100. I have arrivals of 120. Arrivals are exceeding service capacity, so it's overloaded. The x-axis here is looking at variability. So in the x-axis, I am varying the variability of your patience time distribution. And in the y-axis, I'm plotting queue size. This is the low priority queue size because the high priority queue size, well, I'm taking them first. They're close to 0, so no reason to worry about them. And what you can notice, one of these is predicted. That's my light blue. One of these is simulated. That's my dark blue. I'm within 5% all the way down the board. So what you should be thinking now is the formulas seem to be pretty good. I haven't done a full robustness check in terms of like how many servers, how does it vary with different distributions, but we can take some kind of faith that it's working pretty well. Okay? The other interesting thing this brings up, and now I'm just going to do a little aside, I'll call a fun aside for anybody that knows queuing, is why does queue size decrease as variability increases? So when I learned queuing, one of the things I learned was that variability hurts. And if I think about standard queuing formula, we've got the Polachek-Kinchin formula, and if you remember that, variability increases, queue size increases. We've got Kingman's heavy traffic approximation. If you think about that, variability in inter-arrival times increases, variability in service times increases, queue length increases. And I'm suddenly showing you something where queue length is decreasing in variability. Well, that's interesting. So why is that? Well, as variability increases, in this setting with these abandonments, the same number of jobs abandoned, right? I have a mass conservation. The amount abandoning is lambda j minus bj mu j. That's independent of my variability. That's the stuff that I don't have room for. That's not changing. So if that's the case, if that's not changing as variability changes, the jobs that abandon must be doing so sooner. And the fact that they're doing so sooner means that my queue links is actually going to decrease as that variability gets large. So that's sort of a fun little thing to notice here. Okay, and now we can come back to our original motivation, which is, what is this fluid control problem? So we have an overloaded system, because if you don't have an overloaded system, you don't care as much about the scheduling. Also, our approximations are working for overloaded. Okay, so what's happening? The cost structure, remind you of the cost structure. The cost structure, we had holding costs for customers in class J, and we had an abandonment penalty per customer that abandons. So this first term here, this is the cost coming from queue links. So CJ is the holding cost from the queue link. This is my approximation for the steady state queue length. This is my approximation for the steady state queue length in the system. The second term here, AJ is the cost I'm incurring from losing customers. And I'm multiplying it by the amount of customers, my approximation for the amount of customers, or the amount of fluid that I'm losing. And so what do I want to do? I said B, there's a relationship between this B and the scheduling control, which we will discuss, but right now we're saying if we nail down B, that's going to translate into a scheduling control, and we'll be able to say whether or not that's static priority. So I want to minimize my costs over all B in this set of feasible server effort allocations. the other motivation from the question from the talk. When am I going to get a simple index policy, right? I want to think that I've removed the exponential assumptions, the structure of my policy is robust, and I'm going to get the same thing. When is that going to happen? Okay, let's do one thing. Let's think about if CJ equals 0. What's going to happen if I don't have any holding costs and I only have abandonment costs? I just wiped out that complicated QJ function. I just have this. It's the AJ times the amount of fluid that I'm losing. Well, let me write that in another way. I have one part that I really can't do anything about. That has nothing to do with the scheduling control. And I have another part that does have something to do with the scheduling control. That's the BJs. And right about now, I bet you can eyeball this and tell me what the solution is going to be. Good. I see people nodding. So suppose the classes are labeled in order of your A mus. What do you want to do? Well, you want to serve the highest cost classes first, and the ones you're going to ignore are the low cost classes. So you have an LP solution that assigns maximum server effort, the BJ equals rho j, to as many low index classes as possible. So the solution to this control problem is a vector B. How am I going to write that vector B? Well, let me define J star. I want to assign maximum server effort to as many low index classes as possible. So J star is going to be the first time these rho j's exceed 1. So that's basically telling me the class is less than J star, I can serve them. The class is more than J star, I don't have enough capacity for. So I could also write this out as B star. So the first J star minus 1 components, these are my fully served classes. And the workload coming from each class was rho j, so there's no reason for me to serve more than there is. So I've got these fully served classes, that's the rho 1 to rho J star minus 1. Then above J star, I've got these classes that I ignore. They're not served at all. They're my low class classes. I don't care about them. And then I have at most one class that is a partially served class. And so any remaining capacity, that's how much I use for this partially served class. What does this motivate? This looks a lot like if you do a static priority CMU type rule and you rank the classes in order of these in their A mus, that if you think about the server effort allocation, well, what does the server effort allocation have to be to each class? Well, to these fully served classes, it better be the amount of work that's coming in. You're clearly not doing anything to the unserved classes. And there's one that you're maybe partially serving. So this is what a static priority solution looks like. So we've answered the first question. Here is one situation in which static priority scheduling should work well for you. And that's actually kind of nice. There's no conditions on the abandonment distribution. The observation we've just made is if you have a system, you don't have holding costs. The only thing you're going to do is penalize for abandonments. Then a static priority should work pretty well for you. And I'll add one more commentary there. I think it makes a little bit of sense. There's a lot of situations where we see holding costs, but if you're going to have customers abandon, it's actually kind of natural to remove the holding costs, and you're penalizing yourself when you lose the customers. So this is maybe it seems restricted because I moved the QJs, but it's also kind of an interesting observation. Okay, but it's not that I don't care about holding costs at all. So let's go back to what happens if I have holding costs. I still have this term. You know, we did a calculation for this FJ. It was a reasonably analytically tractable thing, so I should be able to get somewhere. So let's continue with my question of when does the solution motivate static priority scheduling? The first is if there's no holding cost. We just saw that. Now, there's a lemma in our tutorial paper because we're showing you what can you do with this fluid model. Well, one thing you can do is you can solve a fluid control problem. And what do we see as the properties of QJ? You can notice that if the patient's time distribution has non-decreasing hazard rate, so IFR, increasing failure rate, then my QJ is concave. Otherwise, if the patient's distribution has non-increasing hazard rate, so decreasing failure rate, then QJ is convex. And let me connect that back. So for an increasing failure rate distribution, this is meaning the customers become less patient as they wait. For a decreasing failure rate distribution, this is meaning the customers become more patient as they wait. So that's my key lemma. If the QJ is concave, then this M star is going to be achieved at a feasible vertex, which motivates a static priority scheduling. In particular, it's going to be a static, state-independent ranking of your classes, and that type of scheduling rule will perform well for you. On the other hand, if the patient's distribution has this non-increasing hazard rate, so the DFR, then the QJ is convex, and what does convex mean? Well, now your M star can be attained at a non-vertex feasible point, and that's going to be inconsistent with static priority scheduling. You're not going to get this B vector that's rows and then zeros. It's maybe going to partially serve all of your classes. And we have numeric examples to show that that does indeed happen. Oh, and I also mentioned to see a recent paper by Long, Shimkin, Zhang, and Zhang for a GMN plus GIQ. They noticed a similar split. They're using convex costs, and they're looking at a generalized CMU rule. So slight difference, but there's definitely a commonality in the observation here. Okay, so where are we? Let's take a breath for a second. We've actually done a lot. We started with this multi-class GGN plus GIQ. We observed, we want to solve a scheduling problem. We observed that, like, wow, we don't even know how to write the evolution equations for this system. This seems hard. Okay, we know how to write them, but they're difficult to track. Solving a control problem is not going to happen. So we said, okay, so let's look at this fluid model. We talked about what the fluid model was. We characterized the invariant states of the fluid model. The invariant states are related to the mean Q length. Invariant states are giving us approximation for the mean Q length and mean rate at which customers abandon. That gave us this fluid control problem. This fluid control problem was quite analytically tractable. So that was kind of nice, because we went from this system that was pretty hard to this very analytically tractable fluid control problem. And we figured out what the server effort allocation is. We can solve that and figure out what the optimum server effort allocation is that minimizes our cost. That's my B star. So what I still need to tell you is, how am I going to schedule in my stochastic model? So I need to give you a scheduling policy. And what I'm going to do here is I'm going to offer a weighted random buffer selection policy. And the reason I flashed this slide up again is I'm not going to rigorously make the connection. I will show you one theorem from our technical paper that lets you know that that weighted random buffer selection policy that I'm about to show you does indeed hit the right invariant state of the fluid, does indeed hit the right fluid model. Weighted random buffer selection, what is this? Well, if I have this proportion of server effort, and I'm thinking about what is the absolute easiest thing I could do, because let me start out with the dead simplest thing. It would be a coin flip. Okay, so I'm going to coin flip. Here's my different classes. I have an available server. When that server becomes free, the available server next serves class J with probability Pj, if possible, and the Pj's have to sum to 1. Why do I say if possible? Well, provided you kind of make a reasonable choice for your P's, provided you don't say, let me bias the coin so that 99% of the time it comes out at class 1, and 1% of the time it comes out somewhere else, well, then you'd be trying at class 1 a lot. So provided you don't do something sort of, provided you do something reasonable, for the most part, when you flip the coin, you're going to find somebody there waiting, because we're thinking of an overloaded case. Otherwise, you're going to have to specify what you do. What are you going to do? Well, the way we're going to specify it, this is technical. I'm not promoting this as the best thing to do implementation-wise, but one thing you can do that gives you some nice properties in that fluid model solution is you flip your coin, you try to serve class J. If there's a customer there, great. If there's not a customer there, you're going to look at class capital J. If there's a customer in class capital J, you will serve him. If there's no customer there, you're just going to do nothing. So it's possible that you have some idling. It is possible that this rule allows you to have a customer waiting that's not J, that's not class capital J, but somewhere else, and you just let him sit. Why are we suggesting that? Because that rule turns out when you go to your fluid model and you add the appropriate equation, this is the appropriate equation. And why is that the appropriate equation? Well, D sum, I don't think I defined that. D sum is the total cumulative amount of fluid that's departing. So this is the cumulative amount of fluid that's departed between S and T, and my coin flip says PJ proportion of that should be from class J. And so I have these upper and lower bounds because I have to worry if the Q-link's positive or zero. And so I'm going to combine this with this equation that is basically say I'm never going to let class J, capital J idle, but that's the only one. The reason I do that is that gives you a nice regulator mapping, and when you go to prove your fluid model solution is unique for this policy, it's a pretty straightforward regulator mapping proof. So I know I have a unique fluid model solution. I'm emphasizing this. Remember, before we didn't have uniqueness. Once you nail down your policy, you want to make sure your fluid model solution is unique. So I've nailed down a policy. It's unique. The reason I have this little fidget in my scheduling rule is because it gives me a very nice uniqueness proof there. The other observation I want to make, you may be sitting there and saying, wow, really? All she's telling me to do is flip a coin? But why do I like flipping a coin? This simple scheduling rule hits your entire range of invariant states. So let me look at this observation after some work. For any B, if I give you any feasible server effort allocation, the WRBS policy that sets PJ like this has invariant state defined by B. So if you solve your fluid control problem and you get a particular B star, now I've just told you what the P you should use in your WRBS scheduling policy. You should use that P. You should use the P determined by this. And then you're going to get a fluid model solution. We've got the fluid model solution, plus you're going to have to add this additional equation. You'll get uniqueness in your, and you'll get uniqueness. Okay, so the other reason we like this policy is that it has, it covers the full range of invariant states. So anything you could possibly get out of the solution to the fluid control problem, we know how to tell. We can tell you how to schedule. Okay, so weak convergence. Basically, this is from the technical paper. This is again to convince you. This is that we have something that rigorously connects between the fluid model with WRBS scheduling, the stochastic model with WRBS scheduling, and the fluid model with WRBS scheduling. Basically, the conditions are the same, and as in the other theorem I showed you. The one thing to point out is we now need the hazard rate of the abandonment distribution to be bounded above. I agree that I don't like that assumption. In the other multi-class paper, it's consistent with it is consistent with the assumptions made in the literature in multi-class GGN plus GQ scheduling. And it's basically coming into play when you prove the uniqueness result. So what is the theorem? So you have a distributional limit point of a sequence of fluid scaled state processes for this WRBS policy. Then X nu eta is almost surely a fluid model solution for your input function E. The input function E is coming from here. And WRBS policy P, it has unique law, and you have weak convergence to that fluid model solution as your number of servers goes to infinity. Okay? So this is the theorem supporting what happens with WRBS. Okay, so I need a time check. Okay, I think I have about 20 more minutes, and I wanted to say we've kind of done the main things being we've seen the fluid model, we've characterized the invariant states, we've set up a scheduling policy, we've characterized the invariant states, we've solved the fluid control problem, and we've gone between the solution to the fluid control problem and a scheduling policy for your stochastic model. So that's sort of like a main thrust here. But I wanted to say something about non-overloaded systems, because if you think about something coming from the beginning of the talk, there were two motivations. One was we've solved exponential for overloaded settings, and when I remove the exponential assumptions, what's going to happen? So we've sort of answered that question. You have to be a little bit careful. Sometimes you get the same state independence index rule, sometimes you don't. The other thing that we noticed, if you kind of remember that literature, was that even in the exponential setting, if you look at critically loaded and not overloaded, we see evidence that you might need a state-dependent policy. So I think it might be interesting to start understanding what's a little bit of the intuition for why you might need a state-dependent policy when your system capacity and demand are close together, and whether or not what you do in the exponential case is going to carry over to a general case. So I want to say just a few words on that to kind of wrap up the talk, and that's also going to give you a sense of where a lot of open questions are if you're looking for stuff to think about. The first thing, if you just want to ask yourself, here's my system, I want to think about scheduling, are state-independent policies enough? One way to go about it is you can quantify the amount of overload in your system by solving for beta in an equation like this. So you have your system, you know how many servers you have. I'm assuming you can estimate your arrival rates. I realize that might be a subject of another talk, but let's pretend you know and can estimate your arrival rates, and same thing for the service rates. So then you could solve this equation for beta. If your beta is very large, what do I mean by very large? Well, 5 definitely. You feel pretty comfortable that your system is overloaded. That means you feel pretty comfortable that the fluid control problem we looked at, and whether or not that fluid control problem results in a state-independent static priority scheduling rule, is going to perform for you. If your beta is small, if your beta is closer to 0, then not totally clear. Okay? So what about for small to moderate beta? And I admit that there's some gray area here. I don't have an exact rule for when beta is large versus when beta is small, but it's clear that if beta comes out being closer to 0, you're probably not in an overloaded regime. So what happens then? So a few words on why you might need a state-dependent scheduling rule. I'm specializing back to the exponential case, so I'll say the exponential case, and then I'll kind of show what happens when you move away from exponential. I'm also specializing to all the, regardless of the class, the service rate is the same for all classes. A2 is greater than A1, theta 1 A1 is greater than theta 2 A2, and I'm going to ignore holding costs. This is definitely a case where I would get the static priority rule, and my overloaded system would tell me to prioritize class 2 because the A2 is greater than the A1. I've got this is a situation where I have that A mu rule and my mu's are the same. Okay, so my fluid control problem tells me prioritize class 2. Another thing I could do in this system is if I wanted to approximate this with a control problem that includes variability, I wouldn't look at a fluid control problem because that's all deterministic. I would look at a diffusion control problem. I'm not going to show you the diffusion. I'm going to let you believe me that in the background there's a diffusion control problem, includes a Brownian motion, it approximates the variability, and I'm going to show you what the solution to that is. And you can see some references if you want to see a little bit more about that. X-axis is total number of customers in the system. Y-axis is telling me the percentage of class 1. So you can think about it as how you would implement this as a tracking policy. If you know total number of customers in the system, how many do you want to be class 1 versus class 2, then you're going to do a scheduling policy that basically sort of tracks this percentage. And let's think about this. So if I just gave you this parameter, and you walked into this and you hadn't heard anything I said, and I said which class to prioritize, I think one thing you might tell me is that, well, if I look at my revenue loss rate, that's determined by the theta 1 A1 versus the theta 2 A2. So I'm going to prioritize class 1. Okay, so let's optimize for this revenue loss. That's class 1. And if I prioritize class 1, there shouldn't be any class 1 customers in the system. So that's why this orange line is sitting here at 0. But what happens when I have sort of a lot of customers in the system? Well, then if you look at my parameters, the theta 1 is going to be has to be greater than the theta 2. So then I'm going to optimize drift. That's going to be class 2. This side is now consistent with what you saw as the solution to the fluid control problem, because I'm telling you to optimize class 2. What's happening here? I'm optimizing drift because class 1 has the higher drift rate. If I kind of change and I have all the customers in the system being class 1 because I'm switching my priorities, then I'm incurring some short-term pain. I'm letting those guys abandon. But in the long term, I'm putting myself in a better steady state for the system, which is a steady state that is kind of down here more often. So this is definitely, it's not a greedy policy. It's something that's forward-looking, and it's coming out when we include the variability. And you can kind of, if you extend that intuition to all possible parameter situations, so you make a little 2x2 box, you're going to see that if you have a nice alignment between your revenue loss and your abandonment costs, you'll get a priority rule versus a threshold rule. Okay, so that's exponential. We saw that in the fluid setting that you might want to be a little bit careful using intuitions from Markovian systems to going to general distributions. So that theme's going to come back here. So let's think about what might happen if I change this last M to a G. I'm solving an approximating diffusion control problem. I'm not showing you that. You can look at the paper if you'd like to see it. So this is a QED regime motivated scheduling policy. I have A2 greater than or equal to A1, and I'm going to assume this abandonment distribution is IFR. And let's try to think about this scheduling policy. I mean, one thing to observe, it is definitely not threshold, because you could say that threshold is still pretty simple. Maybe I've moved away from state-independent static priority rule, but I think we're pretty comfortable with threshold rules. So would threshold work for me here? Definitely not threshold. What does this mean? So x-axis is total number of customers in the system. I'm plotting the solution to the diffusion control problem is giving me my desired percentage of class 1. Where is this coming from? So I'm going to begin by prioritizing this more costly class 2, the A2, and I'm going to hold the backlog in class 1. Okay, so that's what's happening here. But as the total number of customers in the system decreases, remember this hazard rate is increasing. So the hazard rate is increasing. That means at some point I start having too many class 1 abandonments, and I'm going to want to split the server effort a little bit so that some goes to class 1 and some goes to class 2. But eventually, since class 1 is cheaper, the intuition for our fluid control problem kicks in, and when you have a lot of customers in the system, you're back to prioritizing class 1. So we get this interesting U-shape emerging, definitely different from the threshold. You can sometimes have discontinuities in this. It depends on the IFR, but this pattern where you can start prioritizing one class, then do some mixing, then go back to prioritizing that class, that's coming from this combination of increasing failure rate and this, this ordering of the abandonment costs. There's not really any solid mathematical foundation for this. So we guessed at the diffusion control problem. We didn't prove convergence. If you sort of want to think about some mathematical issues behind this, I would say there's a lot of open questions going on. This is, again, guessed at diffusion control problem. The solution to the diffusion control problem is solid. How do we know how well this scheduling policy performs? We did a lot of simulations. One of the things we saw in the simulations is you do get improvements over the threshold. So the question you might want to ask yourself is, even though you moved away from exponential, if you keep that threshold form, maybe you can do pretty close. At least in certain settings, we saw you couldn't always do close. So again, it just says reason to be a little bit cautious when you're moving away from the exponential abandonment distribution. Okay, so I'm getting a little bit close to the end of time. So this is about when I was going to conclude. And what do I want you to remember? What have we done? Well, we developed a fluid model relevant for a multi-class GGN plus GQ. It's relevant under any reasonable scheduling control. So you think about that fluid model. We have a theorem that connects the stochastic model to the fluid model. And what you need is you need some kind of reasonable scheduling control without too much oscillation, and it can't see the future. We characterize the invariant states for that fluid model when the arrival rate is constant. We demonstrated numerically that the fluid model invariant states well approximate the steady state mean queue length and abandonment rate. That allowed us to formulate and solve an approximating scheduling fluid control problem to determine our optimal invariant state. And we provided sufficient conditions for this fluid control problem to motivate static priority versus non-static priority scheduling. And I really mean state-independent index policy. And then we talked a little bit about, at the end, about what's the difference between this overloaded setting and this, this setting where you're not overloaded. It's more like your demand and your capacity are approximately equal. Okay. And at this point, if there are any questions, I'm happy to take them.
How difficult would be to extend this to a case where you want to
maximize service levels in terms of?
The percentage of customers that are waiting queue less than X amount of time.
So you would need to translate, so the formula for the queue length is only mean queue length. So I'd have to be looking at the diffusion control problem where I can incorporate some variability. Oh, I'm sorry. The question, I should repeat the question. The question is, how do I include service levels in this? Because I might want to promise I might want to promise 80% of the customers served within 10 minutes. So that's not something that we're going to be able to cover because we've eliminated the variability in the fluid model.
So I have a question about the index policy review and the abandonment rate, IFR versus HR. So when the abandonment rate and decreasing abandonment rate, isn't it more natural rather than head of line scheduling to do tail of line scheduling? That is, the customer who's most vulnerable to abandonment is the one most recently arrived.
Is it?
If you do that, do you now get an index policy in the decreasing?
This is an excellent question. Within a class, it's quite possible that it's better to do the tail of line scheduling. Critically, to develop this fluid model, we had to assume the head of line scheduling. So within a class, we had to assume head of line scheduling. There's a paper in the single class setting by Basambu and Renhawa that suggests the opposite, what you just said. However, for this particular situation, I need to do the head of line scheduling within the classes.
So in your fluid control problem, if you could just observe the queue length, the fluid control problem would be quite easy. It was only because you needed to write the queue length in terms of the B parameter. So if you had some sort of like max weight type policy, like we'll take the queue length and we'll put it into some function and use that to decide what to use, would that give us an easy solution to the fluid control problem?
So the question is, if I could observe the queue length, then would that make it easier for the scheduling control problem? And I think by observe the queue length, you mean I could observe the queue length over time, I can get an estimate of the mean.
No, I mean observe the instantaneous queue length. So right now, what's the queue length? I'll make my scheduling decision based on that. Because your scheduling policies were not using that.
Yes, so the point here is that I don't need to observe the queue. So you said, so would it help me to observe the queue length? I'm trying to develop a set of scheduling policies where I don't need to observe the queue length. That's the point. In terms of would that help me, what I really need for the control problem, what I'm trying to get at is how do I get the prediction of what the scheduling control does to the queue length? And I'm not sure how to get that mapping from just observing the queue length. Have I understood your question correctly? Okay.
I have a question on the fluid limit. Can you have the same limit if the patient's distribution is actually zero? I know you have these assumptions on the hazard rates. If the patient's is identically zero, you can have the same amount of fluid limit.
So the question is if the patient's is identically zero, meaning I can't tolerate any waiting, so then I'll be in a loss system type situation. Then there's no potential queue. So we didn't exactly do this, but I suspect that what's going to happen is if you look at the paper that's tracking, the part of the fluid model that's tracking people in service, that's going to survive. But the ADA measure and the bit that's relevant to the queue, that is not going to survive. So that's not in our paper. This is sort of me speaking as a guess. But I would imagine that what does survive is the new measure, and the dynamics of that new measure should be, I think, somewhat close. But it's an interesting question to follow up on. Okay, well, thank you very much.